Okay, so I want to talk about a periodic table again. We kind of left it yesterday at the periodic table. So periodic table is, very organized regarding how the elements fall into place. And you're going to see over the semester and in your next chemistry class, we'll be using this periodic table a lot. Now, the one that's in your lab packet is a pretty good one. It's the one that I use. It's the same as this one. It isn't, I didn't photocopy it. This is another version, but basically, this one and the one in your lab packet are both what we're going to be using in here. And the difference is, well, two areas. One is a technical area that's different, but also the decimal numbers are rounded to two decimal places. When you get in 1A, they're not going to be rounded to two decimal places. And 2A, depending on who your instructor is. But anyway, in my class, this is the one we're using. This is the one I use on the tests. That you're going to get a copy of this on your next test as one of the pages in the back. All right, so let's look in more detail now about this. Okay, on every periodic table, there is a minimum of certain things. And some periodic tables have more information than others. So this is kind of the minimum. Actually, this is almost the minimum. Okay, so we've got okay, so we've got a symbol, a one or two character symbol for every element. Now it's very important to notice that if it's a one letter symbol, it's uppercase. If it's a two-letter symbol, it's an uppercase and lowercase. No exceptions. If it's a two-letter symbol, always uppercase, but the second letter has got to be lowercase. Let me show you why that has to be. Okay, this is carbon monoxide. This is cobalt. Entirely different substances. So this is carbon monoxide, and this is cobalt. So make sure when you're writing these symbols, you make sure your second letter is lowercase. Quite a while ago, probably 15, 20 years ago, I had a Coast Guard student. And he was just getting out of the Coast Guard, but his job in the Coast Guard, he used to inspect container ships. And by international law, there is no lowercase. Everything is uppercase. So he was doing like for 5 years inspecting these container ships. And he had to keep a log and all this stuff. So he was in the big time habit of doing everything uppercase. I said, you're gonna have to change that. It's not gonna work in chemistry or physics. So, and in fact, let me tell you one story about him. Who's watched Breaking Bad? Anyone? Okay. What was in the bathtub that fell through the floor? Remember, what's the assistant's name? Jesse, you're supposed to go to the hardware store and get some hydrofluoric acid. Okay, and when he came home, they filled up the bathtub with hydrofluoric acid because it was going to be used to dissolve stuff. And he splashed it on the outside of the tub, and then the hydrofluoric acid ate through the floor, and the whole bathtub came flying through the floor. It was pretty wild. Well, on this container ship, when you inspect the container ship, you have to wear a hazmat suit, and they're made out of this fabric that is like impregnable to most things except hydrofluoric acid. So this guy was inspecting this container, and he saw this drip on his arm, And then all of a sudden, there was a hole in the fabric. And he looked up and there was a hole on top of the container, and there was a hole above that, a hole above that. Well, apparently there's some hydrofluoric acid that started leaking about 20 containers up. And it worked its way down, all the way down. He ended up with a scar on his arm about the size of a quarter because it ate into his flesh. It was bad. So anyway, he was the one that I was instructing lowercase second letter. Anyway, cool guy. All right. So some periodic tables will have the full name of the element. Now, when you get to 1A, it's not going to have the full name. It's just going to have the symbol. And there are two numbers in every box. One is a integer, and that is the number of protons. The other is a decimal. Also, this is called the atomic number. A non-decimal integer, yeah. Or you could write non-decimal. Because that's the number of protons, and you can't have a fraction of a proton. That's why it's a whole number. Okay, the decimal number is kind of complicated. It's the average of all naturally occurring isotopes. Okay, just write that down, and then I'll talk about what an isotope is. We've already mentioned it once, but I'm going to get into it in big time detail. Okay, all right. And there's some other things as well. Okay, there are groups. Groups are columns. And every column has certain chemical characteristics that are the same. So everything in that column is the same. For example, we have sodium and we have potassium. They have similar characteristics because they're in the same column or group. Now you're gonna have to know 4 groups on the periodic table. First group is called the alkali metals. The second group is called the alkali earth metals. Over here on the far right are the halogens. The right one is called the noble gases. Okay, so they're the alkali metals, the alkali earth metals, halogens, and noble gases. Now, every group has a name, but none of the other names are used very often. These are used often, particularly the halogens and the alkali metals and alkali earth metals. Those are used a lot to generalize everything in those groups. And noble gases are used fairly regularly, depends on the context. Okay, now you've only been introduced to this for 5 minutes. Let me show you how useful that information is. Okay, I have high blood pressure. I'm under, I take meds for it. It's like everyone my age takes high blood pressure meds. And the doctor says, cut back on your salt intake. Now the formula for sodium or salt is what? NaCl. Okay, the chloride is what makes it salty. This has to go with it because it's an ionic solid. I'm going to talk about what that means. So I'm in a quandary. I cook a lot and I like to eat. And of course, if you like to eat, you have to season your food, right? So I have a quandary. How am I going to minimize the salt intake in my diet, yet achieve the saltiness I need for seasoning? Okay, if we look at the periodic table where sodium is located, what is underneath it? Potassium. Okay, so if I can use potassium instead of sodium with the chloride, I'll achieve two things. I'll eliminate the sodium, which causes the high blood pressure, and I still have my chloride saltiness. So if you go to the grocery store in the next couple days, you go to the spice aisle, find salt. And right near it is going to be light salt. And guess what light salt is? Potassium chloride. Now, does that make sense? And it's because they're in the same group. Who's watched Chernobyl, the series? Anyone? Oh, if you haven't watched it, it's excellent. It's long, but it's excellent. And the science is like 99% accurate. Got a lot of politics in it. It's very interesting. And one of the problems whenever you have a nuclear accident is you make radioactive strontium, SR. And what happened in Chernobyl, when the explosion occurred, it threw up a lot of radioactive dust called fallout. And then it drifted over Europe and it was a mess, truly a mess. Okay, the problem with strontium, notice it's underneath calcium. When strontium falls down into the pasture, and we have cows foraging in the pasture, they consume radioactive strontium. Guess where strontium ends up if it's a female cow? The milk. Now, the problem with radioactive strontium is it's underneath calcium. Calcium is important for what in your body? Bones. And what is made in the marrow of bones? Red blood cells. So what happens is the strontium is taken up by the cows. Strontium, radioactive strontium gets in the milk. And when people drink the milk, they ingest radioactive substance and it's absorbed into their bones. Hence, radiation sickness is frequently associated with leukemia. And that is why, because of the radioactive strontium. And again, it's because it's in the same group. Same group. So that's why it's absorbed like calcium. Another interesting phenomenon that you know now, because you've taken my chemistry class, is look at carbon. Carbon is the most common element in the body, along with hydrogen. And a lot of your body parts are made of carbon. So frequently, when they make body part replacements, they don't use carbon, they use what? Silicone, because Silicon is underneath carbon, so it has the same chemical characteristics as carbon. That's why silicone is used. So anyway, that's what's kind of cool about groups, chemical groups. Okay. So that's going vertically. If we go horizontally, that's called a period or shell. Now there are 7 shells or 7 periods, and the only thing you can say about the period is the atoms get smaller as you go across. So the trend is decreasing size as you go across. Okay. Now there are certain characteristics of the elements within the periodic table. And they're kind of divided along this black squiggly line. Okay, to the left of the black squiggly line are called metals. To the right of the squiggly line are called, guess what? Non-metals. Okay, and the elements along the squiggly line have characteristics of metals and non-metals, and those are called metalloids. And metalloids, again, have the characteristics of a metal and a non-metal. Now, metalloids are extremely important. Can't emphasize that enough. Guess what industry is based on metalloids? Huh?
Smelting.
Smelting. That's not what I was going for, but yes, they're involved in that. What else? What other industries?
Electronics.
Yes, they're the basis of transistors. In 1947, Bell Labs in Illinois invented transistor. 1947. Before that, we used vacuum tubes. Vacuum tubes are glass-based transistors. They get very hot because you have to heat up an element to boil off electrons. They're very inefficient. The first computer had 10,000 vacuum tubes. It was also the size of this room. And secondly, they had a room this size to cool it. Literally 2 rooms this size, and my phone has more power than that thing by a long shot. It was developed for calculating ballistics of ships' cannons. That was its lease in life. Okay, so in 1947, Bell engineers using metalloids, germanium specifically, developed something called a diode. And the diode is the first transistor. So metalloids are really important. Yeah.
Metalloids.
They're on either side of the squiggly line. So the way I want you to identify metalloids is like this. Because depending on what periodic table you're looking at, some people class a metalloid as a metalloid and some people don't. So it's just basically concept of a metalloid is it takes on the characteristics of both a metal and a non-metal. Now, in your next test, I'm going to give you a periodic table, and you're going to be asked to identify the parts. Metals, non-metals, metalloids, alkali earth, alkali metals, halogens, and noble gases. Okay? Halogens, and then the next column over are the noble gases. So halogens are here, noble gases are there. I know it's kind of busy now, but So on your test, make sure you bring highlighters so you can identify all this stuff. Okay, any questions about the organization of periodic table? Yeah, absolutely no. I'm going to give you a periodic table. What you have to memorize are the groups though. And the difference between metal and a non-metal and so much easier than memorizing the periodic table. So his question was, are we supposed to memorize the periodic table? Not in my class. Now, in your next class, depends on the instructor. They may have you memorize the top part or not at all. We have something called a smartphone. In 4 seconds, we can find out anything we want. We have AI. Yeah. They're along either side of this black squiggly line.
Okay.
Okay, so let's talk now about some of these elements. Let's look at carbon. Now, we look at carbon on the periodic table. Notice there are the two numbers we already talked about, 6 and 1201. When we write an element, normally we reflect the atomic number or the number of protons on the bottom. And on the top, we reflect the isotope. So this is number of protons. This is the isotope or atomic mass. Now, unfortunately, most periodic tables have the 6 on the top and the 12 on the bottom. But that's only on a periodic table, and it varies from periodic table to periodic table. So on the bottom is always the smaller number, number 1, number 2. That's the number of protons. So the number of protons determines what element. We change protons, it's a different element. Now, in nuclear chemistry, they change protons all the time. So in nuclear chemistry, the elements are changing, going through transmutation all the time. Now, the alchemists were trying to do that back 600, 800 years ago. But we do it all the time in nuclear reactors, atomic bombs, in the atmosphere. When solar energy comes in, gamma radiation comes in into the atmosphere, it messes with nitrogen, changes it into a different isotope. So what is an isotope? Okay, for example, we have carbon 12, carbon 14. They're both carbon. They're both carbon. That means they have the same number of protons. They have 6 protons. So what's different about them? Yeah. Neutrons differ. Exactly. So how do you know how many neutrons there are? Well, this is P plus N. So if the total number of protons plus neutrons is 12 and 6 of them are protons, how many neutrons? 6 neutrons. Carbon 14. Now, carbon 14, the top number is going to be 14, not 12. So how many neutrons does carbon 14 have? 8. So isotopes differ in the number of neutrons. So the protons are the same, neutrons are different. So that means the chemistry of carbon-12 and carbon-14 is identical unless it involves the mass of the element. Then they're not the same. For example, when we, right now, the big controversy with Iran is, do they have enough uranium to be weapons grade? Okay, weapons grade uranium is uranium-235. The most common one is uranium-238. 235 will blow up, 238 won't. So what, during the Second World War, during the Manhattan Project, there was a place in Tennessee, I guess, somewhere in that region, where they actually processed aluminum ore to get rid of the 238, keep the 235. Now, they don't weigh the same. The 238 weighs more because it has more neutrons. So they put it in a centrifuge, a very expensive centrifuge, and spun it really fast. So what happens, the heavier 238 uranium went spitting out, and the 235 stayed in the middle. So that's how they purify uranium. Yeah. Why is 235 unstable? It's the ratio of the protons and neutrons in the nucleus. It has to be a certain ratio. If it's not that ratio, it's unstable. And so 235 ratio of protons and neutrons is not stable, or in 238 it is. Now, to make a weapon, you have to have 95% 235. To make a nuclear power plant uranium, you need like 20%. So what they do is they process it to 20%, and they can use it in a nuclear reactor, or they process it more for a weapon, up to 95%. Now, Hanford up in Washington is where, and during the Manhattan Project in World War II, they purified the 238 to 235 to make it. Then they sent it to New Mexico to make the actual bomb in Los Alamos, New Mexico. Very, very secret. Very, very secret. So they ended up making 3 bombs. They tried one as an experiment and it worked. So then they dropped the other 2 and ended the war. There's a lot of controversy about that. A lot of the controversy lies around, was it necessary to drop the bombs? Some people say yes, some people say no. But anyway, it all has to do with the isotope of uranium. One's stable, one's not. What happens is the 235 breaks up into 2 more stable elements plus 3 neutrons plus energy. Lots of energy. Because some of the binding force, keeping those protons next to one another, is given off. That's where all the energy comes from. Pretty wild stuff. Okay, so anyway, unless the reaction is something involving the mass, the chemical characteristics are the same. Uranium-235, uranium-238 chemically act exactly the same. You can form a gas of uranium with fluorine. It's UF6, hexafluorouranium. And it's the same for both, but one's heavier than the other. Hence, in the centrifuge, you can separate it. Okay, so that's isotopes. And you identify the isotope on top, the top number. It's kind of a weird superscript, but it's the top number. So you can have That would be carbon 14. And now there's ways to write carbon 14. You write out the word carbon dash 14, or you write it like this. Now in this worksheet, you're going to be doing both. Okay, so does this make sense in this isotope stuff? Okay, so let's look at this worksheet I gave you. So this is the handout. Everyone needs to get this handout. Huh? Well, people came up. So raise your hand if you don't have this handout. So raise your hand if you didn't get one. Okay, there's a couple over here. And if you look on the back, the answers are on the back. Okay, so what I've done is I've given you the minimal amount of information and we're going to fill in the rest. Okay, one other thing I want to talk about before we do that. There's something called a neutral atom and an ionic atom or ion. Okay, a neutral atom, the number of protons equals the number of electrons. With an ion, protons do not equal electrons. Hence, there's a charge. So if there's an ion, I have to tell you it's an ion. It's not intuitively obvious what it is. And I also have to tell you the charge on the ion or on the ion. Because some are positive, some are negative, depending on the balance between the electrons and protons. Whatever's more dictates the charge. If you have more protons, charge is going to be positive. More electrons, charge is going to be negative. So this chart I gave you, these are all neutral. That means the protons and electrons are equal. The atomic number and the number of protons is always the same. No exceptions. So protons and atomic number are interchangeable. The symbol again, bottom number, the smaller number is the number of protons. Top number is the isomer. This, for example, this is boron 11, and that's made up of P plus N. Well, we know P's are 5, so how many neutrons does boron 11 have? 6. This is pre-calc math. What's the atomic number for boron here? 5. How many protons? 5. How many electrons? 5. What's the atomic mass of this particular isotope? 11. And then the name is going to be, right, boron 11. Now, what I'm going to give you on the test is going to be a subset of this table with missing boxes. So make sure you're comfortable. And then on the back are the answers. So let's do another one. Are there any questions about these numbers? Okay, so let's just choose one. Let's do 31. This one here. Okay, what's the atomic number for this one here? What's the atomic mass? 68. So 31 plus 37 is 68. Okay, how many electrons? Because protons, electrons are always the same with neutral compounds. Atomic symbol, what is atomic symbol 31? Find on the periodic table. Gallium. So gallium is going to be 31 on the bottom, 68 on top. That'd be gallium 68. Now I have an ion version of this as well. So the only difference between the ion one is there's a charge involved because protons does not equal electrons. Okay? All right, so why don't we go ahead and work on this? And if you've already, I know some of you are whipping this out already, this is what I want you to work on. It's really important you get these numbers down and their relationships. Okay? So any questions about how we got these again? Okay, so go ahead and work on these for the rest of the period. That's what we're covering today.